So in this video we're going to look at scaling a sensor. So if we have a tank that has some kind of liquid or something in it, we'll just call it water here. And so we have an analog sensor, and we want to kind of know the sensor is going to tell us whether the tank is full or empty, or where within the sensor range that it is. So what we want to do here, this sensor is going to output 4 milliamps when the tank is empty or at 0%. And then the tank is going to output 20 milliamps when the tank is 100% full. And so when we do scaling, what we're doing, number one, is we're looking for the slope of this line first. Okay, so the slope of the line is the rise, the amount in the y minus the amount in the x. So if we look, then we see that the slope, is going to be 20 milliamps minus 4 milliamps divided by 100% minus 0%. Right? And so the slope of that then would give us 16 milliamps per percent. Divided by 100. So 0.16 milliamperes, 0.16 milliamperes per percent. Okay, so for every 1% the tank level goes up, we're going to have an increase of 0.16 milliamperes. So this is also known as the resolution of the sensor in terms of the actual sensor compared to the percentage of material within the tank. And so we also, though, have to calculate the intercept, right? So the intercept B now is y1 minus m times x1, okay? Or we could also use the y2 minus m times x2. You could use either one of those equations to calculate B, but typically the y1 x1 is the best choice, because usually one of these values are in fact 0, as we see here. So remember, this is our x1 and this is y1, because we're going from percentage into milliamps, because what we want to see is how many milliamps we're going to be feeding into our PLC, right? So we're going to have this analog current sensor signal coming into our PLC. So this is going to be our PLC over here. And so we want to know how many milliamps are actually coming into the PLC. So that's why I have milliamperes on top in this case. All right, so if we calculate B, then we would take x1 is 0, and so we simply have to, we would have 4 milliamperes minus the m, which this is our m value here, okay, times x1, which is 0 percent, but this is milliamps per percent, so the percents will cancel out and we're just left with milliamps. All right, so the slope, or our equation for milliamps is equal to 0.16 milliamps per cent times X percent plus 4 more milliamps. So when the tank is empty, our sensor is still going to give us 4 milliamps. And then when the tank is full, our sensor is going to be giving us 20 milliamps. Okay, so if we take this, let's just watch and see what happens, right? So we take Y in milliamperes equal to 0.16 milliamperes per percent times 100% plus 4 more milliamperes. Okay, so the percentages disappear, and so you have 100 times 0.16, which is going to give you 16 milliamperes plus another 4 milliamperes, right? And so at 100% then, we are going to be getting 20 milliamperes coming into our PLC. All right, so that's just kind of a double check. Now, if you're going to be putting this into Blackboard, when you do your scaling, okay, I am very picky. I didn't do it right here, but what you want to do is keep 5 significant digits for your scaling equation. For your slope and your intercept, they should be 5 significant digits. And so therefore, if I was actually going to put this into Blackboard, it would be Y is equal to 0.16000. That's 5 digits right there, okay? Milliamperes divided by percentage times X, which is a percentage, plus 4.0000 milliamperes. That is the 5 digits. Okay, in this case, it just turns out that it's got a lot of zeros, but most of the time it probably isn't going to work out quite so smoothly. And so you need to make sure you keep 5 digits at least here, so that when you actually calculate how many milliamps or whatever that you're calculating for your Y value, you can then round it up to 3 digits and not run into round off error. Okay, so so make sure you keep 5 digits for your scaling equation. Alright, so now let's say that we're feeding this into our PLC, and the PLC has an analog to digital converter which supports 8 bits. Okay, so it's not a real high quality analog to digital converter here, just 8-bit one. These are actually very affordable to get an 8-bit one, and it usually gives you decent resolution. Sometimes you need more, but if your resolution doesn't have to be that critical, a nice low cost 8-bit is a good choice. And so now one thing you have to remember here though is even though our sensor is going to send out 4 milliamps when we're at 0, but the analog to digital converter is actually always reading from 0 milliamperes up to the 20 milliamperes. Okay, and so it's doing the conversion based on 0 milliamperes to 20 milliamperes. And so when we look at this, so we need to like find out, you know, okay, well, what would be our current signal when we're getting 4 milliamperes? And so again, we can calculate our slope, okay? And our slope to find counts. So what we have here, we have we have 8 bits, which gives us 2 to the 8 possibilities. So 2 to the 8th possibilities means that you have 256 unique possibilities. However, the smallest possibility is 8 zeros. Okay, and so you're basically at 0, and the largest possibility is 8 ones, which is 255. All right, because one of these 256 unique possibilities is 0. So your range is actually ranging from 0 to 255. So we actually have 255 counts. Okay, technically this is not bits. We have 8 bits to store the number in, but we have 255 is the maximum number that we can have. So what we're really looking at is the unit there would be counts. What is the count? Okay, and so and then it's going to be count per milliampere. All right, so since our PLC is going to read from 0 to 20 milliamperes, no matter what the sensor is giving us, okay? So it really doesn't matter that the sensor is only going from 4 to 20. All right, so we're going to have counts, so we're going to have 255 counts minus 0 counts divided by 20 milliamperes minus 0 milliamperes. Okay, because this is actually what the card is reading. The card is reading from 0 milliamperes, not 0 milliamperes, okay? And so that gives us 255 divided by 20, which gives us 12.750. Okay, so again, we want 5 digits. So 12.750 counts per milliampere. Okay, so every time the signal changes by 1 full milliamp, we're going to see 12.75 counts. Now, one thing to keep in mind, right? Remember that the analog to digital converters do not round up. Okay, so they do not round up. So if it increased 1 milliampere, the count would increase by 12. It won't increase by 12.75 because the count is an integer value. It's not a floating point. So you can't have 12.75 as an integer value. You're not allowed decimal points in integers. And analog to digital converters convert into integers. All right, and then if we look at the slope, remember or not the slope, but the intercept, right? The intercept for this would be B is y1 minus m times x1. Well, if you look at this, x1 is 0 milliamperes, and y1 is 0 counts, so you'd have 0 minus m times 0, so your B ends up simply being 0. All right, but remember we need 5 digits for that. So if I was going to write this conversion, so if I'm going to write counts, so if I wanted to write these counts, okay, it would be 12.750 counts per milliamp That's my 5 significant digits times X times the milliamperes or x is in milliamperes, excuse me, that's the units of x, okay, plus the intercept of 0.0000 counts, okay, so that 0 and then 4 zeros after the decimal point is my 5 digits that you need to put into Blackboard for it to be counted perfectly correct. Okay, 5 significant digits. Okay, so now the next question comes in though. We will never see 0 counts as long as the sensor is working correctly, because remember, the sensor is actually going to output 4 milliamperes. So the first question becomes, what is the count when the tank is empty? Okay, so the tank is empty, so we're at 0% on our tank, which means the sensor is outputting 4 milliamperes. So the question is, what is the count? Well, we just punch it into the equation here. 12.75 times our 4 milliamperes, and again the units of this are counts per milliampere, count per milliampere, right? So the milliamperes are going to cancel, and I'll be left with counts, and then we're going to add the 0 on there, which of course doesn't change anything. All right, so inside of our PLC now, we're going to be reading the decimal value of 51 counts. Okay, so our analog to digital converter is going to be giving us an integer value of 51. Okay, 4 times 12.75 is going to give us 51. All right, so now if we wanted to, inside of our PLC, let's say inside the PLC now, we want to create a compute equation that is going to tell us what the percentage of the tank is. Okay, so what is the percentage of the tank? So how full is our tank? So we have here, okay, we have here on the left side is going to be our percentage. So we're going to be at 0%, meaning we're empty, or 100% when we're full. And inside of our analog to digital converter, we're going to have 51 counts when the tank is empty. Right? And we're going to have 255 counts when the tank is full. So now we can come up with a equation to tell us what is the count, okay? What is the count for a given percentage, okay? Or what is the percentage depending on how many counts that we have. So you can go either way. So let's say that we know the tank is 37% full. Okay, so we want to find out how many counts that is. Well, if that's the case, then we need to write the equation. We need to write the equation in terms of, we want to know how many counts given the percentage. Okay, so our slope, we would calculate the slope M is going to be, we want counts as the output, so counts go on top. So it's going to be 255 counts minus 51 counts divided by the percentage, which is 100%, minus 0%. And so if we calculate that, right, we would have 255 minus 51 divided by 100. And so we get 2.0400. Remember, we want 5 digits. So that is going to be 2.0400 counts per percent. Now, once you have this value, if you wanted to know the other way, so if you also, let me do it in a different color here. Let's say that you also wanted to know, well, what is the percentage if I know the number of counts? Well, it's 1 over this. Okay, so it's 1 over this m here. And so you just take the reciprocal of that to go the other way. So I'll just kind of do that right now. So we can, you can go either way very easily. All right, and so that gives us 49020. Okay, again, 5 digits. 49. All right, so the M in the opposite direction is 0.49020. That's the 5 digits. Remember, the 0 to the left is required, but it's not a significant digit. It's simply a warning telling us that there's a decimal point coming. Okay? And so the units for that then are going to be percent per count, right? It's just a reciprocal, percent per count. All right, so now up here though, we had to calculate the B. Okay, so now we have to calculate B. Okay, and B is the Y1. And up here I was doing counts was on top. So Y1 would be 51 counts. And then times my M, or minus my M. Okay, minus my M times my X term, but my X term is simply 0. All right, so when we write this then, up here for this one, this is going to be 2.0400 counts per percent. Okay, and then that's going to be multiplied times X percentage. And then we're going to add, that's a positive, we're going to add the 51 counts, okay, but we need 5 significant digits, so we're going to add 51.000, okay, so when you put it in a blackboard, I need those 5 digits, and the units for that would be counts. So now, if we want to go the opposite direction though, so if we wanted to go from the counts over to the percentage, right, we already had our M down here in blue, but we need to calculate our B term for that. All right, and so again, B is Y1 minus M times X1. So in this case, we're looking like down here, but our Y1 is our 0. Y1 is the 0, and then we're going to have a minus. And of course that was in percent. Okay, 0% minus, and then there's this minus here, M, which is this value here. So I'm not going to rewrite that whole value, but M times the 51 counts. Now notice this negative sign, okay? Because we at 0%, we have a positive 4 milliamps coming in, which means that we have this value of 51. So we need to make sure we subtract that off. Okay? So we're going to subtract that off of there. So we're going to have, this was 0.49020 times the 51, and the 51 is counts. Okay, and this was the units for this was percent per count. percent per count, and so the counts cancel, and we'll be left with a percentage, but it's going to be a negative percentage we're going to have to subtract back off of there. All right, so that's the 4902 times the 51, and it turns out to be 25%. So we're actually got to subtract off 25%. Okay, so that's going to be 25, and since this is a scaling equation, it's going to have 3 extra zeros to give me 5 digits, and the unit for that is percent. So when we're going from percent, so this top one up here in this magenta color is going from percent to counts. The blue is going from counts to percent, and so it's going to be 0.49020% per count times X and however many counts that we need minus 25%. Okay, so that'll give it to us in percentage. All right, so as I stated earlier, let's say then that we wanted to kind of know if the tank is at 37%, what is the value inside of the what is the value in our PLC? What's the analog to digital converter reading inside the PLC? So that's this equation up here. So we would punch that in here. So we would go in there and we would take the 2.0400 counts divided by a unit of percent, and we're going to multiply that times the 37%. And then we're going to add on the 51 more counts. Okay, and that'll tell us the value that's actually in our analog to digital controller. That's that integer value that the PLC is actually reading. Okay, and so we just flip over to our calculator software here and punch that in. So 2.0400 times 37% plus another 51 counts. Okay, now that, when I do the calculation there, you see that it is 126.48 counts. That's not the answer, okay? Because the converter doesn't do the fractions, okay? So the correct answer is just simply 126 counts. This is an integer value. There's no decimal point here, all right? So the answer is simply 126, okay? I don't even care if this calculation would have came up to be 126.9999999 counts. The answer is still simply 126, because remember, the way analog to digital converters work, you have to cross that threshold, okay, for it to move to the next count value. And so even if the value was 126 with nines forever, it hasn't crossed the threshold, and so it's not 127. You do not round up, okay, and you do not put decimal points, because the analog to digital converter only gives you an integer, right? This is an integer value here. All right, so now if we wanted to put a compute statement, okay, because this is what we're actually getting inside our analog to digital converter. So this is the value we've read into our PLC. So let's say that we have a tag called count, and that tag value then is 126. So now let's say that we want to actually know, well, what is the percent? How full is the tank? Okay, so we come back down here to this equation down here, and we can calculate how full the tank actually is. So we just take this 126 count and stick it back into this equation to get it back into a percentage. And so this would be our compute statement. So inside of the PLC, right, we would have our ladder logic, and we would have a compute box here. Okay, and the destination of this, there would be a destination, and we would have a tag here, which would be a floating point real value called percentage. So we'd create a tag percentage, which would be a real floating point type number. And our compute statement then, our expression now is going to be this equation where I guess I'm just going to call this is my tag. Okay, so if this is what I named my tag, not sure that's a great name, but if that's what I named my tag, my expression down here would be 0.4902, and there's no reason to throw in the zero into that last zero into the ladder logic's expression, but we would multiply that times our count. So remember, count is actually now our tag, okay, or whatever name that we gave it, okay, and so that is our tag. And then we're going to add, it's actually subtract the 25. So again, I mean, you could type in the 000 there if you wanted, okay, but you don't necessarily have to. So this is the expression we would put into our compute statement, because the 126 is coming in. That's what the analog to digital converter is giving us, is this 126 count. And so what we really want to know is, okay, well, what is that percentage, right? We don't care that it's 126 counts. We don't care that it's however many milliamps, and I can go back up and we'll find out how many milliamps it is here in a minute. But we want to know what is the percentage, right? And now remember, we actually came up with this count because I used this equation and said, well, 37% is going to give me a count of 126. Okay, so we're going to, so if count is 126, right, and then our percentage tag now was going to hold the value if we punch this in. All right, so we got the 4902 times the count of 126 minus 25 counts is going to give me 36.765. Okay, so it's going to give me 36.765%. All right, and now remember, we started out with 37, but what happened here was there was some fraction here. It didn't break that threshold, and so we're actually going to be reading just a little bit less than that because it hasn't actually crossed the threshold yet. All right, so our real value reading in from our compute statement is going to be 36.76. And now this value is kind of a final percentage, so this should only be 3 significant digits. And so if I was going to put this into Blackboard, I would put in 3, 6 point, and now this 6 would round up that 7 to an 8. So 36.8 space percent. And this would be my final value that I would put into Blackboard. All right. So for the slope M and the intercept B, those should always be 5 digits. But when you give final calculations, okay, if the calculation has units of count, there's no decimal point and there's no rounding up. But if it is converting back into a real value, then it would actually round up a little bit. Okay, so, and you go to 3 significant digits into Blackboard. All right, so now if we wanted to calculate how many milliamps that was, we could kind of come up here, and I guess I didn't do the reverse of that equation up here. So I found out how many counts, but I didn't find out how many milliamps. So what I would have to do is take this slope and flip it and calculate the intercept. Okay, and let's see, that in this equation here we didn't have any intercept. All right, so if we wanted to determine the milliamperes, I could just take the reciprocal of this in here. So I could say Y, change colors here. I could say like Y in milliamperes, because I knew that I had 126 counts down here, is going to be 1 milliampere divided by 2.75 counts times the 126 counts. Okay, so the counts will cancel, and there was no intercept here because it was just 0 and 0 in this case, so I don't have to worry about the B. So that would be 126 divided by 2.75. And so that would, all right, so yeah, sorry about that. It's 12.75 counts. 12.75 counts. That it was when I drew the box around it, I couldn't see the 12s, right? Well, you can see it up here. It's 12.75. So I need to 126 divided by 12.75. When you get 45 milliamps, you know you did something wrong. Okay, so it should be 12.75 there. So that gives me 9.88 milliamperes. Okay, so again, in this case, this is in milliamps, and you can have a fraction of a milliamp. So it would be 9.88, because I only want 3 significant digits. So 9.88 milliamperes. Okay, so that's how many milliamps that we have going to percentage. Okay, so and we could do this equation up here also. All right, so because remember I said we had 37%, so we could actually stick it up here in this equation here and stick in 37% times 0.16 milliamps and add another 4 milliamperes. Okay, 0.16 times 37 plus another 4 milliamperes, right? And we're off a little bit there, okay? And remember again, because I used the 37% here, But remember, when we did the calculation down here, our analog to digital did not round up. And so that's the difference between this calculation of 9.88 milliamperes here and this calculation using the full 37%. Because remember, because our analog to digital did not round up, we're actually only getting a reading of 36.8% instead of the full 37%. And that's the difference here between these calculations. So this one here was 9.92. At 37%, I came up with 9.92. But at 36.8, this is actually 36.8, because even though the tank may be at 37%, because we only have an 8-bit converter, the closest that we could get was 36.8%. Okay, so we couldn't actually detect that 0.2% increase, or that's already in the tank. We're not detecting it yet. We need more before our count is going to increase. All right, so but this is just a simple example, just trying to show you how the scaling works. You don't, most of the time you don't really have to worry about the milliamps, because you really want to scale from your tank being 0 to full to the counts inside the PLC. And the milliamp is kind of a median here, and you know, a lot of times you can skip any sort of middleman sort of calculations, but sometimes when you're testing or debugging, you may need to know what those are. And so I walk through the whole thing, scaling each one of those.